This is lecture 44. We're going to talk about the derivation of a stochastic differential equation. Okay, so remember last time we talked about an SDE having this form dx is equal to mu plus b dw. So the terms mu is given by the expected value of delta x divided by delta t. Our b is our covariance term, so this is equal to v to the 1/2, where v here is given by this formula. Okay, so for the example that we're going to work with, we're going to think about a simple birth-death model. This is from lecture 36. The birth-death model was given by this formulation. So here, the probability that you lose one is given by this birth rate times delta t. Probability that you gain one is lambda times delta t, and saying the same is 1 minus that probability. Okay, so here we have our stochastic model continuous time Markov chain here. So what we want to do is we want to actually write the transitions in table format, which is going to help make our life easier when we're starting to derive our stochastic differential equation. So this is what I mean by writing in a table. So we're going to talk about what change is there and what's the probability of that change. So here our change, we're going to say the first change that we can have is the change of a -1. What's the probability this is going to happen? This is going to be mu s delta t, so here this should have been an s and this should have been an s, sorry about that. And then the change of 1 here with the probability lambda s, and the change of 0 is p3 is 1 minus the sum of all those probabilities. Okay, so we look at the first term mu. Mu is given by this expected value of delta x divided by delta t. So this is the table that we had before, which is going to help us in terms of writing this. So what we need is we need E of delta S, and so if we have that, we can find our mu. So the formula for E of delta S is just the sum of all of our probabilities times the change. So if we go through this, we have our change here is -1. The probability of that is my mu S delta t. Here the change is 1. The probability is lambda S delta t. And then we have a change of 0, and here's our probability. So if we kind of combine these, what we're going to get is a lambda minus mu times s delta t. Once we have that, it's easy to calculate mu. Mu is just this value divided by delta t, or lambda minus mu times s. So now we look at the covariance term. So this is our b of t x term. So in order to do this, we need the covariance. The covariance in general is given by the expected value of delta x transpose minus the expected value of delta x, and then the transpose of that expected value of delta x. Normally we shorten this, and so we just, the second term here is of order delta t squared. So normally we estimate our covariance as just this first term. So we're going to calculate our covariance as this E of delta x transpose. So for our birth-death example, again, here we have our table, so this table comes in handy. So when we're calculating our E of delta S transpose, now we're going to have the probability times the change transposed. So here, if we look at this one, we have our probability is mu S delta t. Our change is -1, and our change transpose is again -1, because here we just have basically a one compartment system. Then we have our probability, and then we have, sorry about that, we have our probability here, and then we have it times the change transpose, and then the probability of the third one times our 0, so this just simplifies to lambda plus mu s delta t. So once we have this, then our v that we have is just what we already found divided by delta t, so we just had the lambda plus mu s. And our b that goes into our formula is the square root of that, or v to the 1/2. So sometimes it's going to be a matrix, which you're going to see it next time. So it's not as easy to find the square root when it's a matrix, but this is just a one compartment. So here we had our general form, we had our mu that we found, we had the b that we found. We can put it all together, and so for our simple birth-death process, we have ds is equal to our mu times dt plus our b times dw. So next time we're going to do derive a stochastic differential equation for a two-state problem, which starts to get a little bit more complicated, but following the simple steps that we followed for this one-state problem, it should be easy to do.